Muchas gracias. Buenos dias. I want to thank the organizing committee, and especially Naraldo Rojas and Paola and Javier for the invitation to speak today. I'm a chemical engineer, so being at a mining conference is going to be a little different. I don't speak geology, I speak chemistry, so it's going to be short and sweet, and we're going to talk about resource evaluation in the lithium industry. Okay. Of course, we're a U.S.-based company, so we have to have this disclaimer that the lawyers make us put in there. A little bit about Li3 Energy. Currently, we are managing an exploration/development program on 6 different lithium brine properties, 3 in Argentina, 1 in Peru, 1 in Chile, and 1 in the United States, Nevada. So in looking at our program, we are doing the parallel program between exploration and development, and so our key objectives is time to market. So we want to manufacture a product for the lithium-ion battery industry. So we're going to talk a little bit about, I'm going to talk a little bit about the requirements for that industry. And then the second main objective is to be a low-cost lithium producer, and the evaluation criteria in looking at a brine resource that will lead us to that low-cost position. A little bit about lithium applications in the lithium battery industry. Got a little drawing there with the cathode and the electrolyte are the 2 main components of a lithium-ion battery. The lithium cathode is specific to a specific manufacturer's requirements. Could be manganese, could be lithium iron oxide, but and the choice is yet to be seen for the electric vehicle, what will be the predominant cathode material. But there is one key that we do know is that lithium will be required in any lithium-ion battery system in the cathode material. Different cathode materials require different purity levels. There's lithium carbonate, which is 99% pure, and lithium carbonate that is 99.5% purity. There are cathode materials that require a different lithium species, the lithium hydroxide monohydrate. But as I said before, all the starting materials and raw materials for these products and these batteries will be lithium carbonate. The other side of the LIB, the lithium battery, is the electrolyte. This is the fluid that allows the charge to go back and forth between the cathode and the anode. Lithium LiPF6 is the only choice currently right now as a lithium electrolyte. It's manufactured in Japan and China. It requires a high purity lithium carbonate product, and currently the product that is being sold into that market, lithium carbonate, is 99.9% purity. So with that basis, it led Li3 to 3 potential products, and the specifications are the 99% purity product, the 99.5 product, and the 3 nines product. This slide gives you a little feel for the impurities, that's what we're going to talk about when we look at our brine evaluation. Magnesium, as you can see, doesn't change much between the 2 purity products, but when you go to the 3 nines material, you have a step change from 100 down to 5. This is done in the processing of the lithium carbonate, so it's not affected by the brine process or the raw material, brine raw material. Potassium is 500 ppm for the 99% material, and you see a step change to 50 with the 99.5, and then down to 10 for the 99.9. The sulfate is basically similar to and the 99 product in the 99.5, 500, 300, and then again you see another step change down to the high purity product. Sodium is variable, and in the processing, the specification for the standard product 99 technical grade product, I'm going to call it, is 1,000 ppm. The 99.5 is 600, so you get a step change there, and then a major change down to the high purity product. Calcium is also variable between the three products and does take a major cost step change to get to the 10 ppm level. So that sets the stage for the product that we want to produce. Now we go back to the resource, and I just want to comment a little bit because the majority of people in this room are going to be hard rock miners, and the lithium brine is a fluid product, and it's very different from the hard rock mining. So that's when we look at our chemistry and location are very important when selecting a lithium resource. In brine chemistry, you have to it has to be very carefully evaluated. You can't just take one or two ratios and say, okay, this is a good resource and this is a bad resource. The thing to keep in mind, just to simplify the chemistry here, is lithium is the last product that comes out of the brine. So you have to remove everything else before you get to the lithium. So some of those impurities have a cost. Those costs are associated with raw materials to remove those impurities, and then the lithium loss that's associated with the removal of all those products that have to come out first. And then a very important criteria to being a low-cost producer is that some of the impurities generate a byproduct credit, some more than others. And I'll get into this in more detail. A typical brine analysis is made up of the major components that we saw on the specification sheet: lithium, sodium, potassium, magnesium, calcium, and boron. These are reported as milligrams per liter. And if you're interested in the method, that's the method that Li3 uses. And sulfate is milligrams per liter, chloride, and density. So when we take surface samples or we take well samples, this is the criteria that our initial criteria for selection. So I'm going to start and go down through the impurities and talk a little bit about the criteria that we use, and then summarize with some ratios that are a good quick look if you want to take a look at a brine process. Lithium recovery from the well out in the salar to the end brine, which is the brine that is fed to the lithium carbonate plant, is less than 50% recovery. Precipitation of the salts in the process take the lithium with it, because in each step you're concentrating the lithium value and you're also removing solids. And as you remove those solids, you have liquid entrained in the solids, and that takes lithium with it. And obviously, lithium is the valued product here. In the sequence of a typical, and I want to stress typical because every brine resource, whether it's in Argentina or Chile or Bolivia or in the U.S., has a different component structure, thus it has a different processing. So I'm going to talk in general terms and try to relate back to the main producers of lithium carbonate, which are in the Salar de Atacama. In this process, first of all, you remove the sodium chloride, which is halite for you mineral folks, sylvinite, which is a mixed salt between sodium chloride and potassium chloride. Then, in order to remove the magnesium, we have magnesium hydroxide, which is a byproduct, calcium sulfate, boric acid, And then in the lithium purification itself, once we take the end brine, you also have losses of lithium in the carbonate precipitation. So you can see that lithium recovery, why is it 50%? Because each one of these salts takes lithium with it. And so it's a complex configuration of removal versus managing your removal cost versus your lithium cost. Magnesium is a favored ratio that people like to look at. You read about that. If you read a Lithium 101, they'll say, what's the mag to lithium ratio? So I caution you to focus on just one ratio. It's a combination of the ratios. Magnesium is one of the major costs of brine purification, especially in Argentine brines. The process, a little chemistry, is we use hydrated lime. We add it to the evaporation ponds. The lime reacts with the magnesium chloride to produce magnesium hydroxide solid and calcium chloride. The magnesium hydroxide is removed by settling, filtration, and different types of separation technologies. It is a major technology and cost factor in evaluating a brine. And from my experience, each brine is a little different with the magnesium removal. Sulfate is a good thing and a bad thing. And it has sulfate is required because we just added lime to the process, so now we have calcium chloride, so we now need to remove that calcium chloride. Keep in mind we've got to remove everything that's in there before we get to the lithium. If the brine doesn't contain enough sulfate, then we have to add sulfate. So here again, we've got to have enough sulfate in the process to remove the calcium, or else we're going to have to bring in sodium sulfate, which can be added. The reaction is sodium sulfate solid with the calcium chloride from the mag removal step to produce calcium sulfate, gypsum, which is a solid, which is easily removed, and sodium chloride, which goes back into the solution. Also, if sodium sulfate's not available, it depends on your economics. You can also use sodium carbonate, but obviously the cost factor of sodium carbonate is much greater than sodium sulfate. But and the reaction of the sodium carbonate is with the calcium chloride in the liquid stage, and then calcium carbonate being produced, and sodium chloride. As I mentioned, sulfate is a good and a bad thing. If you have an excess of sulfate in your brine, then it results in a sodium sulfate and potassium sulfate precipitation in the pond systems. This can disrupt the whole pond system and basically lowers your recovery of potash and also of lithium recoveries, because these salts are are precipitating out and taking the lithium with them. So just to summarize sulfate, you've got to have enough to remove the calcium, but you don't want to have too much. Boron must be removed because boron is a poison in the carbonate for the cathode manufacturers and some of the other downstream lithium chemicals, especially in the manufacture of lithium metal. Boron is a poison in the electrolytic cells for that in that manufacturing process. Some of the boron does drop out, depends on the chemistry, with the extra calcium that we've added from the magnesium removal step. But in most processes, a secondary step of boron removal must be added. The two main technologies used for that are solvent exchange and ion exchange. And as I mentioned, sometimes there is a cost-benefit ratio to the removal. Depending on the concentrations of the boron in the brine, there is a potential that boric acid can be recovered as a valuable byproduct. Potassium. Potassium forms sylvinite, which is sodium chloride, potassium chloride. It's removed in the evaporation ponds, and standard technology, potash processing technology, can be used to remove, separate the KCl, potash, from the sodium chloride. Currently, right now, based on the current market price, KCl, and it's fluctuating all over the place, is a good number. A low number would be $300 per ton, and this can affect. This is a direct credit back into the lithium carbonate process. At Li3, we feel like this is the key to being a low-cost producer, is our potassium byproduct credit. In fact, we've just announced recently the acquisition of a nitrate iodine project in northern Chile, basically north of Iquique, or west of Iquique, to where we can use upgrade our potash from our lithium processing plant to produce the potassium nitrate and upgrade the byproduct credit to almost $900 a ton is the current price for potassium nitrate. This has been a successful model for SQM, and again, potassium is the key to being a low-cost lithium carbonate producer. This is a bunch of numbers, but there's some ratios. The magnesium to lithium, potassium to lithium ratio, sulfate to lithium ratio, magnesium to calcium ratio, potassium to magnesium, and sulfate to magnesium. I'm going to summarize it in a little simpler, what's good and bad, whether it's high and low. But this gives you a feel for looking across Chile and Argentina and Bolivia. The Salar de Uyuni this is the lithium triangle. It's referred to by the press. The Salar de Uyuni in Bolivia, the Salar de Atacama with the two major producers of lithium carbonate. So we use this as our benchmark if you want to compare to current producers. We also have FMC Lithium, our Argentine lithium producer at Hombre Muerto, and the chemistry there, and the Salar de Rincon, which is also in Argentina. You can look at some of the major differences, is the mag to lithium ratio at Hombre Muerto, the higher sulfate to lithium ratio in Rincon, and the higher sulfate to magnesium ratio at Hombre Muerto. So, and this was provided. I have to give credit to my good friend Pedro Pavlovich, who gave me permission to use this slide. He said it was also published, so that helped me out. So to summarize the ratios, the key evaluation ratios, is when we look at a brine, we're looking at the magnesium to lithium ratio. High mag to lithium ratio will give you an increased cost, period. High potassium to lithium ratio will give you an increased byproduct credit, so that's a good thing. Sulfate to lithium ratio will basically decrease the potassium byproduct credit and also increase the lithium loss in your process. So it's a bad thing. A high potassium to magnesium ratio will increase your byproduct credit, which is a positive, and a high sulfate to magnesium ratio will give you increased byproduct credit. So in summary, as the world moves to focus, and Argentina focuses on lithium, when when we're looking at brines and when we're looking at new projects, as I mentioned, Lithium-3 has 6 brine projects that we're looking at. We focus on these key ratios to drive our exploration process and end up also becoming a low-cost producer. So I want to thank you very much.